So let's look at the infinite geometric series. So as you would have discovered during the investigations, that infinite is going on and on forever. But what happens when your common ratio is a fraction or a decimal that is either greater than -1 but also less than 1? So essentially it's a fraction, or we could also say that the absolute value of your common ratio must be less than 1. So what they're indicating right here is, provided that r to the n is a fraction or a decimal less than 1, which is referring to the absolute value, then it's closer to 0 as n gets closer and closer to infinity, right? So taking a look at 1/2, if you look at 1/2 squared versus 1/2 to the 1, and what you guys already know is that things are as your exponent gets larger, then that product, that value of r to the n, if r, let's say, is equal to 1/2, just gets smaller and smaller and smaller. And so the larger that your exponent n is, then the larger your denominator is to the n. Of course, it's 1 to the n as well, but 1 to anything is just 1. And so then that's why it's going to approach 0. So we just assume that it's going to get to 0 because it's an infinite series. So we've got our formula right here that we'll use. Again, looking at the fact that r is less than 1. Because of that, we don't indicate that r cannot equal 1, because we already know that if r is greater than or equal to 1, then the sum of the infinite series, geometric series, is not defined. Looking at that overview. So what we have been looking at are the finite geometric series. So that we know where the beginning is, where the end is, what the last term is. Either we know we're adding together 15 terms, or else we know what the last term is. We may not know its term number. On the other end, when we have the infinite geometric series, it can go one of two ways. It can be convergent, meaning that the values are getting smaller and smaller and smaller because our common ratio, the absolute value of it, is less than 1, or else it is considered divergent, meaning that the series is getting larger and larger and larger. It doesn't converge on a particular value. It just gets larger and larger. Therefore, we know already that the sum will be infinite. Okay, so moving on then. So it says, determine the common ratio for each of the following geometric series and state whether a sum to infinity exists. So really where that comes in is, if we're saying state whether a sum to infinity exists, what are we asking ourselves? Is it convergent or divergent? In order to figure that out, we need to figure out what r is. So looking at here, and even do we need to know exactly what r is to determine if it's convergent or divergent? No. Think about, is it actually getting smaller? And so 1 plus 1/3 plus 1/9. We know already that the ratio, common ratio, is 1/3. Therefore, it is convergent. It's a convergent series. So if we're looking at our formula then, and we know that Sn is equal to A over 1 minus R, and R is equal to 1/3. Again, remembering if you can't remember, or if it isn't immediately obvious, you can do T2 divided by T1 or T3 divided by T2. So we've got then 1 divided by 1 minus 1/3, which is of course 2/3. So 1, looking at 1 divided by 2/3, or 1 times the reciprocal of that, which is then 3/2. so our sum then is 3 halves. For B, does the sum exist? No, because r is equal to -5, so this is divergent. No sum exists. When we look at the next one, what is our ratio? A common ratio is going to be -1/2. We can know that it's negative because the signs are switching, negative, positive, negative, and then -1 divided by 2 is of course -1/2. So then we know that this is going to be convergent because it's between -1 and 1. So again, looking at our formula for an infinite series is a divided by 1 minus r, or in this case 2 divided by 1 minus -1/2, or 1 plus 1/2, which is then 3 halves. So 2 divided by 3 halves is the same as 2 times the reciprocal, or 2 times 2/3, which is then 4/3. Looking at class example number 2, if we're given that A is equal to 2 and the sum Sn is equal to 4, we're trying to determine the common ratio. So we know that Sn is again equal to A divided by 1 minus r. So let's take a look, substitute everything in. So we would have then 4 is equal to 2 divided by 1 minus r. If we multiply both sides by 1 minus r, then we end up with, so 1 minus r, a 1, and multiply this side by 1 minus r. So these factor out or cancel out, and therefore we're having to distribute our 4. So we have 4 minus 4r is equal to 2. Subtract 4 from each side, so -4r is equal to -2 after I've subtracted that 4. Divide both sides by -4, so r is equal to then -2 divided by -4, or r is equal to 1/2. Okay, so if we want to look at class example number 3, writing the repeating decimal, 0.07, repeating as an infinite geometric series. So thinking about that, 0.07 repeating is the same as 0.0777777, and on and it goes. So what are we looking at then? Is we are looking at 7 hundredths, then plus 7 thousandths, plus 7 10,000ths, plus, and that just goes on, right? Because this is our hundredths, 7 hundredths, 7 thousandths, 7 10,000ths, 700 thousandths, and so on. So find the sum to infinity in A, and so if we're looking at that, we want to consider what is our common ratio. So term 2 divided by term 1, or we can see that we're multiplying by a common ratio of 1/10. So r is equal to 1/10, and A is equal to 7 hundredths. So then our sum to infinity is S of n is equal to A, or 7 hundredths, divided by 1 minus 1/10, or you could say 7 hundredths divided by 1 minus 1/10 is 9 tenths. So divided by 9 tenths, multiplying by the reciprocal, so 7 100ths times 10 ninths, and then 10 and the 100 can reduce to 1 over 10, in which case we're left with 7 over 90. Some of you perhaps may recall this from an investigation you did when you were in grade 9. So that would be and your fraction, which is, equal to 0.07 repeating. And you can check that, of course, enter that into your calculator, into your graphing calculator, either 0.07 repeating and put a whole bunch of sevens and ask it to change it, use your math button and convert it back into the fraction, or take 7/90ths and say 7 divided by 90, and that will, of course, equal 0.07 repeating. Excellent.